Hello. For the next few episodes, we have a very special guest, Professor Ananthanarayan, who will be speaking to us on the physics of the Standard Model. Professor Ananthanarayan is professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore, where he has also served as head of the department and guided several PhD students, including at least one of my own former colleagues. He did his BTech at the Indian Institute of Technology, Madras. Switching to physics, he then earned a master's in science and a PhD in physics from the University of Delaware in the US. Anant is a member of the editorial board of the European Physical Journal A and the Indian Journal of Pure and Applied Physics. His research interests are in the field of elementary particle physics and quantum field theory. He works both at the frontiers of the standard model and high precision, and also at finding signatures of interactions that lie beyond the standard model, that is, at finding new physics that can be uncovered at the International Linear Collider. He has also worked on dispersion relations, on the chiral symmetry of the strong interactions, and on grand unified theories and supersymmetric models. Anant is a prolific writer, a popular speaker, and a recipient of the Homi Bhabha Fellowship and the Rustam Choksi Award for Excellence in Science. If you have missed some of our previous episodes, I recommend that you watch episodes 20 and 21 on the quantization of the radiation field and Feynman diagrams, and episodes 26 and 28 on symmetry and group theory and Lie groups before you watch this episode. With that, it gives me great pleasure to invite Professor Ananthanarayan to join us.
Welcome, Professor Ananthanarayan. Thank you for sparing your time and doing this chat with us. As I told you, I want to start with a kind of a philosophical question. I know you'll be dealing with it in more detail in your talk, but let me start with lead off with something that arose during our conversation with Professor Arunan last week. He said that in chemistry, it's all about classification. We classify atoms into groups and periods. We classify compounds into organic and inorganic. We classify bonds into covalent, ionic, and so forth. And I dare say this is true also in biology, that classification is a major theme. But we see that in physics, at least the motivation has been presented as one of unification ever since the time of, let's say, Faraday and Maxwell, unifying electricity and magnetism, and then unifying electromagnetism with light, and then more recently unifying electromagnetism with the weak force, and then with unifying the electroweak force with the strong force, and so forth. But I also see, is it perhaps that classification and unification are two sides of the same coin? Because group theory is used to classify the particles into various kinds. So how do you see it, and what do you see as the motivation for for what you study?
Thank you very much for inviting me. I was not. I know that there was a recording of my good friend Arunan's conversation with you, but I hadn't yet looked at it because I was busy thinking about this talk and kind of preparing what to say in our conversation. I think what you're saying is, of course, partly true, but that's not the whole story, because the kind of phenomena that we are encountering in elementary particle physics is also so immense that, of course, there is a classification. And the idea that we want to try to break down our understanding to as few a set of principles as possible. So there is always the notion of analysis, which is to break up things and to first observe phenomena and to gather data about the world around us. And then later, of course, we want to bin that data and then put it into neat pigeonholes, if it is possible, if there is such a pigeonhole principle at all. But and I wouldn't even say it's a motivation, but more like the need to understand what are these fundamental laws which govern the motion. I mean, yes, of course, even in physics, you can have motion of all kinds of things, whether it is man-made objects or whether it is celestial objects. But eventually, we ended up distilling it to a couple of laws, like Newton's law of gravitation and or Kepler's laws. So these things go hand in hand. So to that extent, when a large amount of data was gathered in basically in the 20th century about various elementary particle phenomena, they needed to be organized, and then one had to understand what are the roots or the basis of the interactions among particles. And that is how we ended up with the theme of this discussion, which is what we had decided to call the essentials of the standard model. And what is this standard model? What is so standard about it? What kind of a model is it? I mean, when we were kids, we were all accustomed to going to, let us say, a science exhibition or a planetarium where you would see, a model for, let's say, the solar system with a central object that was supposed to represent the sun and a bunch of little beads representing the various planets, giving you the idea of the scale of the solar system, of the distances between planets, the relative sizes of the planets. But the interesting thing would have been to see moving models where these things would also move. So every model as such is not just a very kind of prosaic description of objects, but also the moving parts, and the interrelationship between those things has to be encoded by the model. So whenever one goes through, let us say, a Wikipedia page on the standard model or something like this, it is a lot of description of this particle, that particle, its properties, etc., without trying to breathe some life into the interrelationship. So my idea in our conversation would be to go through some of these notions of exactly what makes this the standard model, why is it important, and more precisely, one keeps seeing popular science stories that something is consistent with the standard model, or there is evidence beyond the standard model. All this is there in CNN or Quantum Magazine and all that. So the idea of this conversation is, if there is, let's say, a listener who is like 16 years old, class 12 student, or somebody who is from some other branch of science or some other branch of knowledge, or even a layperson with interest in the world around her or him, that they would understand what is meant or get an idea of what is meant by this standard model and what lies beyond the standard model, if at all. And that is what I hope that we will be able to discuss in these episodes. And I must apologize in advance that although I think we had budgeted about 2 hours, it may well be, may take more than that.
It
so
may
let
take,
me apologize.
well, yeah.
Yes.
So what does the standard model deal with?
Okay. So that's what I'll get to. And just like in our UPSC exams or in JEE, there is a preliminary part and then there's a main part. So with your leave, I will start with these preliminaries because I need to define a certain vocabulary and certain expressions and terms without which it would not be possible to talk about what is known as the standard model and what is so standard about it. So,
Sure.
so if you give me the leave, I'll need to share the screen.
Yes,
because I have some notes that I have prepared. And this is going to be in black and white, a little bit of blue because I misplaced my black pen at times and I had to live with the blue. So any coloring can be done by the reader himself or herself with highlighters. I'd also like to say at the outset that
and of course, you're not referring to the color in the standard model.
No, but that also we will get to soon, I hope. But I would also like to caution that everything that I'm saying should be cross-checked with authoritative references, because I would like to basically tell the story with a little bit of shall we say, some content in it, so that everybody has something that they can take home. It may be too simple for some, but they may get an insight listening to it. So this is what. Or somebody who doesn't know anything should not feel overwhelmed at the end of this discussion, but a person should feel encouraged to take it up and try to understand. There's a large number of resources available on the internet, whether it is Wikipedia or pages from CERN websites or Fermilab. All of them have educational material. And I'm sure there are lots and lots of references. So maybe we can begin, and if you permit me, then I share the screen.
Yes, please share your screen, please.
Okay. So thank goodness for all this modern technology. So is that okay?
Yes.
May I begin with this?
Yes.
Yeah. So in order to discuss what we are calling the standard model, which is a quantum field theory based on something called a gauge principle, in order to explain some of the fundamental forces in nature, which are the electromagnetic, responsible for interactions between charged particles, the so-called weak interactions, and then the so-called strong interactions. By the way, these are all historical names, okay? So the name weak interaction, it's actually not particularly weak, but it manifests itself as weak for a completely different reason, not because the coupling constants are necessarily small. In fact, the coupling constants for the weak interactions are basically the same order of magnitude as the coupling constants of the electromagnetic interactions.
So what do you mean by
So the
coupling
weakness,
constant?
so we will introduce all these terms as we
Okay.
go along.
Okay.
For instance, in electromagnetism, the coupling constant is nothing but the electric charge. So similarly, there is a charge that is carried by particles that participate in the weak interactions. So the electromagnetic interactions take place with the exchange of real or virtual photons, which are massless particles, and they are the quanta of light. There are analogous quanta of the weak interactions, which today we know they were discussed, or they were discovered in the laboratory over 40 years ago. They're called the W and the Z bosons, or the Z bosons, depending on what you call, what you prefer. And then the so-called strong interactions, which actually are not so strong because they exist in a different phase, which is called the confined phase, and the microscopic degrees of freedom, which participate in the strong interactions, which are the quarks and the gluons, actually get frozen out. And what we actually see are so-called effective degrees of freedom, such as the protons, neutrons, and the carriers of the internucleon forces, such as the pions and the kaons. The kaons, for instance, are the so-called strange counterparts of the protons and neutrons. Again, these are all historical names. There's nothing very strange about a strange quark. It's just a name that was given by Gell-Mann and Pais about 75 years ago, when they were discovered in cosmic rays.
And nothing
then there are
charmed.
many other quarks.
And nothing charmed about the charm.
Nothing particularly charming. It's just a very nice name that was
But
given.
but the strong force is is strong enough to overwhelm the electromagnetic force at short distances, right? So that
So that's what
probably
happens.
justifies the name.
Yes. So for instance, inside a nucleus, we have protons and neutrons, and the protons repel each other.
The file is getting hidden, and I'm seeing your desktop instead.
Yes. That's because I was not talking about the file.
Oh, okay.
So I was just
Fine. Okay.
Yeah. So I will switch back and forth when I'm actually using the. So for instance, inside nuclei, you have protons and neutrons, and the protons are electrically charged and carry the same charge, and then they repel each other because of Coulomb repulsion. But then the pions which are exchanged among all the nucleons is enough to compensate for this Coulomb repulsion, which is what gives stability to nuclei. So you're right. So, but this is not the fundamental strong interaction, but it's an effective strong interaction due to the exchange of pions and kaons and things like that. So, returning now to the preliminaries, let me just begin with quantum mechanics, which has already been covered by Sukumar in many of his lectures, which are being given to commemorate the 100th anniversary of quantum mechanics, so to speak. I mean, Planck, of course, had discovered the Planck's constant 25 years earlier, but quantum mechanics per se, I guess, is associated with the paper of Heisenberg from 1925, and later, of course, Schrödinger from 1926. So quantum mechanics, which is what we study in textbooks, is a framework to understand the quantum mechanical interactions between particles in certain regimes, one in the non-relativistic limit, where the velocity of particles is much smaller than the velocity of light. The velocity of light, everybody knows, is about 300,000 kilometers per second. And it's a very good approximation to study even, let's say, the hydrogen atom in the non-relativistic approximation, because the velocity of electrons in the hydrogen atom, I think in the nearest Bohr orbit, is about 1 by 137 times the velocity of light. So it's fine. So this number 1 by 137 will follow us around in this discussion.
But we do have to worry about it when we get to the core orbitals of the heavy metals. Like relativistic phenomena, special relativistic phenomena are what give rise to the color of gold and silver and things like that.
Yes. That's very interesting. And also for very heavy nuclei, because for instance, if you take uranium, that 92 times 1 by 137 becomes closer and closer to 1. I mean, that's just one way of trying to understand why very large nuclei, you cannot ignore relativistic effects. But yes, thank you. So, the study of non-relativistic quantum mechanics, especially textbooks and introductory courses, relies on our study of what is called the time-independent Schrödinger equation, which is written in the following way, and it allows me to introduce Planck's constant divided by 2 pi, represented by h bar, so h bar squared by 2m, d squared by dx squared, of psi of x, where psi is called the wave function of the system. And the system is described by a potential that is called v of x, and we are trying to understand the quantum mechanics of a particle that finds itself in a potential v of x. So this is the equation, which is written in this way, and this is an equation that needs to be solved with suitable boundary conditions and becomes what is known as an eigenvalue equation, which can be solved. And when you find the eigenvalues and the corresponding eigenfunctions, then you say that the problem is solved once and for all, and assuming that this differential equation has known solutions. So if it does not have known solutions, then you can solve for these numerically. So if v of x is solvable, then the bound states, so there are 2 kinds of states in non-relativistic systems. They are called bound states and scattering states. Bound states are often very interesting because we can do a lot of good mathematics also, and it's useful for illustrating many of the concepts that we have when it comes to the study of quantum mechanics. So, as you all know, the energy spectrum is given by En, where n runs over a set, and this gives rise to what is known as a complete set of states. It doesn't mean that n has to be necessarily be infinite or anything like that. It depends on the problem, but often it is a denumerably infinite set. And this psi of n are what are called square integrable wave functions, and the set psi n is called the Hilbert space of states of this particular problem. Now, up until this point, I've assumed that this v of x is solvable. Supposing it's not solvable, but there is a small change or corrections to this v of x, And it's actually not just V of x, but V of x times something that makes a problem no longer solvable. And let us represent the so-called correction to this potential or perturbation as some other potential V sub lambda of x. And let us multiply it by a constant lambda. And of course, if you put lambda equal to 0, then you get back the original problem that uh, you started out with. So what would be of interest would be, what are the corrections to this energy E of n due to the presence of this perturbation? And this is done in every quantum mechanics course. The first order correction to each of the energies, the first order correction where the cursor is, to each one of the energies is given by this matrix element of V of lambda, sandwiched between psi of n, where the psi of n are the eigenfunctions of the original unperturbed Hamiltonian. So that's the nice thing. So what you need to know is the entire Hilbert space of the solvable problem, and then that allows you to get this correction at leading order in this parameter that we call lambda. But it doesn't stop here. For very simple systems, actually, we get a further result that the second order correction can also be computed, and it's given by this expression where you have matrix elements of this V of lambda now no longer diagonal, but this V of lambda sandwiched between the state of interest to you given by this n and all the other states psi of m. This is what is known as resolution of the identity, except that there is also an energy denominator that shows up over here, which involves the unperturbed energy levels. So this is very nice that it's possible to get some kind of a series in this lambda and corrections to this energy in terms of the original problem where everything was known. So order by order, you can try to do this. And this gets more and more complicated.
So yes. That's when lambda is small, right? When you have a small perturbation, so that you have a convergence of the different energy.
You hope that it is convergent.
Yeah. Yes. So I was going to ask, is that always the case?
No, it is not at all obvious at all. In fact, the problem that we always ask in interviews is when this perturbation for the simple harmonic oscillator is a constant electric field, the leading order term vanishes, and the second order term you can find, and it stops. You actually get the full answer because it's equivalent to redefining the original simple harmonic oscillator problem by a shifted potential, and thereby you can get the actual correction to order lambda squared in that electric field. So there are all kinds of properties. It depends on the original potential. It depends on the perturbation, etc., etc. So, but this is something that's known in textbooks. It's because that's the reason why I'm motivating it, because we want to now say that in elementary particle physics also similar things happen. So that is the reason for offering this as a preliminary in this particular discussion. And there are numerous examples in quantum mechanics textbooks. And I think working out those problems is real fun. And I think students should work out as many problems as possible in order to, turn these problems into their friends and not turn to AI and ChatGPT to give them the answer, but to actually get involved in calculating these things, because that's how you actually learn this. That said, the problems are not always bound state problems, but very often we have scattering problems. For instance, Rutherford scattering. The scattering problem. And what is of interest to us are the cross sections in scattering problems. It could be a differential cross section, it could be the integrated cross section, etc. And what we do in such problems is to compute so-called matrix elements and then square the matrix element and then use something known as a Fermi golden rule, which is a very beautiful little result, and relate the square of the matrix element, which takes you from a given initial state to a given final state, multiply it with various kinematic factors, and lo and behold, what you get is a cross-section. And a cross-section, when it is multiplied by a flux in an experiment, will give you the number of events that will be seen by a detector that is placed. If it is the total cross-section, then of course it is a total cross-section, or you can have a differential cross-section where you have a detector at a fixed angle theta, and then you look for d sigma by d cosine theta, for instance. All textbook problems. The other kind of problems that one does in quantum mechanics courses are evaluation of lifetimes of, let us say, unstable states of an excited state in atomic physics. And then with the emission of a photon, then, a given excited state can either decay to some other excited state, or it can decay to a ground state, subject to selection rules and all these things. Once again, there is the use of the Fermi golden rule to compute lifetimes. So even in elementary particle physics, ultimately what you measure in any experiment, whether it is a cosmic ray experiment, or whether it is a deep underground neutrino experiment, or whether you put some kind of a detector on top of a satellite, or on the International Space Station, or at the LHC, where you have the experiments CMS, compact muon solenoid, or ALICE, a large LHC ion experiment, or at the ATLAS experiment, a toroidal LHC apparatus. All these experiments, the detectors, what they do is they measure cross sections, they measure number of events, they measure other properties of deposition of particles, such as calorimetric information and directional information. So everything ultimately goes back to the basic ingredients, which is calculations of cross sections, of lifetimes, application of the Fermi golden rule whenever there are interactions. So, for instance, in elements, I don't know, let me now go to the next page and then talk to you a little bit in words about how we go from quantum mechanics to quantum field theory, which is basically something you cannot avoid in elementary particle physics, because, for instance, particles appear and disappear. You may do an experiment with electrons and positrons and collide them on top or with each other. And if the energy is sufficiently high, then in the final state, you may find a muon pair, mu plus and mu minus, where muons are particles, elementary particles, which are exactly like electrons, except they are about 210 times as heavy. And if you switched off the weak interactions, the muons would be stable. Why is this? We don't know. These are all the particles that exist in nature. And unlike in quantum mechanics that I just mentioned in the previous slide, where you have scattering of a fixed target, and then you have a beam of electrons that comes and scatters, and then you have a detector. In elementary particle physics, what you do is you collide E plus and E minus, and out come mu plus and mu minus. So to that extent, what happens is that the energy that is present in the collision of the E plus V minus collision makes a fireball because of interactions described by the standard model. And then this fireball that forms momentarily breaks up, produces mu plus mu minus. It can give you E plus E minus also. It can give you pi plus phi minus. All kinds of particles can be produced. So this is a basic thing that any student has to understand, that the difference between non-relativistic quantum mechanics, where we do not really create and destroy particles. Again, I'm partly contradicting myself, because when you have an excited state of an atom, you are creating a photon in the excited state, decays to the ground state. So a new particle is created, even in non-relativistic quantum mechanics, so to speak. And this was the program of what was quantum field theory is something that you need in elementary particle physics for the reasons that I discussed earlier. And for most part, relativistic quantum field theory will be for scattering problems. Of course, as we just discussed a few minutes earlier, even in bound state problems, there are relativistic effects. And there is a framework for that, for bound states also. And that is what is known as the Bethe-Salpeter theory. But that is not part of what we will be discussing today. So as I mentioned earlier, I hope that the screen is visible.
Yes.
Yeah. So in elementary particle physics, particles can be created and destroyed. And the examples that I gave you, for instance, was a neutron decaying into a proton plus an electron, and what is known as an antineutrino So these are neutrinos and antineutrinos are also elementary particle physics, elementary particles, which do not carry an electric charge, and they only interact in the participate in the weak interactions. Nevertheless, they are of paramount importance because they determine the fate of stars. They are copiously produced in stellar reactions and things of that sort. So everybody today has to know about neutrinos also. Just a point that I wanted to make, that they need not be considered as exotic or unknown particles. And I think even in 11th standard and 12th standard textbooks, they are mentioned, and they are produced, for instance, in the decay of radioactive nuclei. Um, the so-called beta emitters also emit neutrinos as a byproduct. So a neutron is unstable, and the muons I had already mentioned are also unstable, and both of them decay through the weak interaction. The muon decays into an electron, and a neutrino-antineutrino pair, which disappear, which are practically impossible to detect unless you have dedicated experiments just to detect them. So most of the time, the missing energy in reactions is because the neutrinos escape, carrying away the energy. And they were predicted in 1930 or so by Wolfgang Pauli in order to rescue conservation of energy and conservation of angular momentum. Because at that time, the continuous electron energy spectrum was a puzzle. And Bohr was of the opinion, probably in nuclear physics, energy is not conserved. That was a hypothesis, which in the sphere of logic is perfectly okay. But Pauli gave the other hypothesis, which is that of the neutrino, which was later confirmed. So there are other particles, such as the pions that we mentioned, which are the particles, effective degrees of freedom that are responsible for the internucleon force. And pions are also unstable. They also decay weakly. They charged pions decay through the emission of a neutrino and a lepton. So what we do over here is similar to what we talked about earlier in the non-relativistic quantum mechanics context, which is again lifetimes are computed by computing a matrix element for a particular transition from a given initial state to a given final state with the effective Hamiltonian that causes the transition. You square that matrix element and multiply it by other kinematic factors, which goes under the name of the phase space. And then that's how you get the lifetime. It's the application of the Fermi golden rule in relativistic quantum mechanics also. So that would be for decays. The neutral pion, on the other hand, which is a partner of the pi plus, pi minus, and pi zero, together they form what's called an isospin triplet, decays through the emission of 2 photons. It's kind of funny that such a decay exists, because this is a strongly interacting particle. So why should it decay into 2 photons? Well, it does, because of something known as the chiral anomaly, and this is now known for over about 80, 70 years, 75 years, that it decays in this way. And there are other particles, for instance, of great interest would be certain kaons. Kaons are just like pions, except that they have a strange quark instead of just U and D quarks of which the pions are made, and it can decay into either 2 pions or 3 pions. So in particle physics, as I said, you have decays where new particles come into being and old particles disappear, subject to the conservation of energy through the Einstein E equals mc squared, which says that any energy can turn into particles, etc., etc. You can also have reactions. This is something that I mentioned, of an E plus E minus going to mu plus mu minus, which we diagrammatically represent as this. And this is actually a leading order term, again, harking back to our previous discussion, that the interaction you can have at leading order, which is the electric charge in this case. It's not a complete description of E plus E minus to mu plus mu minus, but evaluated in perturbation theory, in a perturbation series, where you have a perturbation in powers of the electric charge. And this is the leading order diagram for this, where an E plus E minus forms of, yes.
Can you define the conventions you're using in these diagrams?
This is not a very good convention, because this is not a Feynman diagram where the particles and antiparticles must have very specific directionalities. So this is just a cartoon over here. Sorry about that. So sometimes, I've not been very careful about this. Thank you for
Yeah, but the arrows and the wiggly
Yeah,
lines.
it is just to say that this particle E plus and E minus hit each other head on. It is just that. It's just a diagram. It is not meant to be taken literally at all. Because then, as you correctly said, but it can all. What can I say? I don't want to say anything more
Yeah,
because
and the wiggly line represents the interaction here, or it represents a force carrier.
so here this is the photon. This intermediate line over here at relatively low energies is a virtual photon that is produced. That's a fireball that I mentioned, which then produces a mu plus mu minus in the final state. If the energy is cranked up, then you can also have the virtual exchange of a Z naught whose mass is about 91 GeV. So then you can have two diagrams, and then you have to sum the two diagrams, and then you would have to take the matrix element of the square of this, and then you can have an interference term between the
Yeah, I
two
think you get to
diagrams.
those later in the lecture.
Yes. So to go back to our previous discussion, and this is something that is heuristic, it should not be taken as in any way rigorous. The unperturbed system is just free particles, which are represented by plane waves, and then the interaction vertex is just the interaction, the electric charge. And so you can have a perturbation theory that you build up for processes of interest to you using a systematic procedure that is known as the Feynman diagram technology. So this is how I connect this to our slide 1 of this preliminaries, where the unperturbed system, the eigenfunctions are free particles represented by plane waves, and they are solutions of an unperturbed analog of the Hamiltonian, which in this case has to be relativistic. And this was already done by Klein and Gordon, and even Schrödinger actually had already proposed a relativistic generalization of his own equation, and their solutions of this relativistic generalization of the Schrödinger equation. The first one was known as what we call the Klein-Gordon equation, which describes free particles that are associated with specific transformation properties under the Lorentz transformations, and that's why they go under the names of scalar and pseudoscalar. This is the quantum numbers of these particles under the Lorentz transformation. So the Lorentz transformation, as you know, is a set of transformations between inertial reference frames, and this is the basis of the Einstein theory of relativity. And there are various representations of this Lorentz symmetries, and it is also intimately related to the spin associated with those particles. So scalars and pseudoscalars carry no spin. The pseudo here stands for the property under reflection. Okay, so if a field changes sign under reflections, it's called a pseudoscalar, and if it doesn't change sign, then it is called a scalar. So one of the aims in my discussion here is to try to explain every single word that I'm introducing, because it's all part of the vocabulary today. So that is one of my fears, is this is going to become very long because I will have to be, pedantic. I would like to be pedagogical, but I may end up being pedantic, although linguistically they are similar words, but content is quite different. So I hope that will not be a problem. So the analogous solutions for particles that carry spin half, and this is known to everybody, and is what is known as the Dirac equation, which is a relativistic equation that describes spin half particles as well as their antiparticles. So it's an amazing thing, this Dirac equation. It describes a spin half particle, so you can have a spin up and a spin down, and it also describes not just the electron, but simultaneously describes the positron as well. So Dirac's equation actually predicted the existence of antiparticles in a way.
And if you can, if you can explain the covariant notation that
yes.
you're using, and the gamma.
Which I've not got there yet. You mean this one here?
Yeah.
I'll get to it. Okay. So I'm just giving some names of equations. that ought to be part of everybody's vocabulary. There are again related equations. There's one called the Weil equation, which may be used to describe neutrinos. There, because neutrinos are also very peculiar particles. Neutrinos observed in the universe are all only left-handed. By left-handed, we mean that if the particle has a motion in one direction, then its spin only points in the opposite direction. So that's called a left-handed particle. In contrast to antineutrinos, which are always right-handed, which is that their spin always points in the same direction. Why is this so? Well, nobody really knows. So this kind of chiral property, chiral as in handedness, Tamil also it is chi, as it is in Greek. Nobody knows why it is like that. So that's the reason why we still call it a model. That is, there are many, many things we just put in. It's like tightening a bolt here and loosening a nut there and so on. We don't today, even today, don't really know the origin of these properties. So there are also analogous equations that govern spin-1 particles. They're known as the Proca equations, which are used to describe the force carriers, which are all spin-1 particles, such as the photon, the W plus minus, and the Z naught, and the gluons. Well, the graviton is also a force carrier, but nobody has seen it so far. But that's a spin-2 particle. In some theories, you also have spin 3/2 particles, and spin 3/2 particles are also known in nature. For instance, there are excitations of the proton that are called the delta resonances, which carry a spin of 3/2 because so-called baryonic matter made up of 3 quarks, each of which carries a spin half. So if you line up all the 3 spin halves, then you get spin 3/2. Simple angular momentum addition, and those are described by what is known as the Rarita-Schwindler equations. So there's a bunch of these relativistic equations, which was a field of study long ago, but a lot of their properties are already known. So as Sukumar just asked, how do you say a few words about this so-called Dirac equation? Now, we already said that this is a relativistic theory. So in the special theory of relativity, we try to treat the time as well as the space-like components on the same footing. Okay, but of course they are not the same. The time direction is unique, whereas we have 3 spatial directions. But we want to at least have a notation where we can talk about all of them in the same breath. And this particular symbol that is used, this is partial mu. This means that this stands for d by dx mu, where mu is a label of the space-time indices, where mu equal to 0 stands for the space-like or temporal direction, and 1, 2, and 3 stand for the 3 spatial directions. Okay, and then there is something known as the metric associated with this, so that you have a proper time element which is given by c squared t squared minus x squared minus y squared minus z squared. All this goes into the definition of this object. But it turned out that merely having these derivatives was not enough to give a proper relativistic equation, but it was necessary to multiply every one of them by 4x4 matrices denoted by this gamma mu, where again mu runs from 0, 1, 2, and 3. And it turns out that in order to have the proper algebra, you can actually populate the various entries of this 4x4 matrices by having block diagonal entries, which are the Pauli matrices. And the Pauli matrices, as you know, are the building blocks of spin, right? This is known again from quantum mechanics textbooks. So this is a very quick way in which you can try to understand why the Dirac equation has to look the way it does and why it manifestly encodes the property of spin also, because the gamma mu's have the sigma matrices, namely the Pauli matrices, sitting inside them. So this is a free particle equation, a complicated one where the psi is actually a column vector with 4 entries that describe spin half up and down for the electron, spin half up and down for the positron. So this is a free equation, and this psi is a bunch of plane waves multiplied by column vectors 1, 0, 0, 0, or 0, 1, 0, 0, etc., which are just column vectors. Such objects are known as Dirac spinors. And when people say physics, what is physics in a word? This sounds like a silly philosophical question. But ultimately, physics has to do with objects and motion among these objects and the laws that govern these motion. And the fundamental quantity associated with motion is momentum and energy, right? So if you want to describe anything in physics, there is some object that you have to define which encodes the energy of the system. And the correct energy functional in this case to describe relativistic physics is what is known as a Lagrangian, named after Lagrange, who is one of the people, early founders of classical physics. So the Lagrangian in point particle mechanics is often defined as the difference between the kinetic and the potential energies. And then there are suitable relativistic analogs of this. And so that's the energy. Okay? And then something that comes associated with the energy, carrying the dimensions of energy multiplied by time, is known as the action. And in fact, the Planck's constant is called the Planck's fluctuation in the interval.
Go ahead, please.
So how do we know that Planck's constant is that of the action? Because E equals h nu, where nu is a frequency carrying dimensions of 1 by time. Therefore, h has to carry the dimensions of energy times time, which is action. Okay. But the point about all this, and this again goes back to the first question that Sukumar had today, is how is it that we try to, do classification and end up with pigeonhole principles? It turns out a lot of physics, due to the work of people like Hamilton, and so many others, is what is known as an action principle, which has been found through decades of struggling with the laws of physics. That there is something called an action principle from which many of the laws of physics can be derived. And in order to have an action, you first need a Lagrangian. And actually, what we call a Lagrangian in particle physics is really something that should be called a Lagrangian density, because it carries the energy, dimensions of energy divided by volume. Okay, so let's just keep that in mind. But it's not particularly, it need not trouble us at the moment.
And the
so
yeah.
Yeah.
Well,
Go ahead.
the four vectors that you introduced there,
Yes.
the A mu, which is the vector potential
Yes.
with the fourth component
Yes.
being the scalar potential,
Yes.
and the F mu nu.
Yes.
Yeah.
Yes. So, going back to our first slide, we said that we need free particles and then we need an interaction term, right? The interaction term is what we had called lambda v lambda. So, if you just have the free Hamiltonian, like the free the equation of a free Dirac particle, it should be derivable from a Lagrangian through an action principle. So if you turn off the electric charge of the electron, then you will end up with this particular combination. As I said, this psi here is a Dirac spinner, and you have to invent a Lagrangian density really, which must have nice mathematical properties. It must involve both the Dirac spinner as well as something known as the Dirac conjugate, which is like taking a complex conjugate and again multiplying it by one of these gamma matrices times gamma mu d mu. And from here, you would get this particular equation if there was no electric charge. But then ultimately, in life, you cannot have any measurement unless there's an interaction. If free particles are free and don't interact with anything, you'll never know that they are there. So in order for us to know that something is there and something will enter your detector and strike a target or something like that, it had better interact with something. For instance, it could interact with, say, the electromagnetic field set up by a heavy nucleus. Okay, so let A mu, which is something that describes the electromagnetic field that is set up by a nucleus, this electron had better interact with it. And how strongly will it interact? It will interact as strongly as the electric charge decides what it is. That is how you get the electric charge over here. And this A mu over here is again something that must have a temporal part and it must have a spatial part, because everything we are doing is relativistic. And let us not forget that Einstein's original motivation was to study the motion of electrically charged particles. On the electrodynamics of moving particles is the name of his foundational paper on the special theory of relativity. So the electromagnetic field had better appear in whatever we do. And it does over here. So this peculiar combination, and this A mu, as we already said, mu must run from 0, 1 to 3, is something from which electric and magnetic fields should be derivable, and we will do that in one of the later slides. Okay. And to make all this look nice, this A mu can't just sit by itself, because it needs to interact with this psi and this psi bar over here. And this gamma mu is needed in order to do that. Okay. So this is all consistent. This is again bunch of gamma matrices. And this is not enough, because what is this electromagnetic field? Does it not have dynamics of its own? Is it just there just to be a handmaiden of the electric field? Well, not quite. We know that electric and magnetic fields also carry an energy, right? So the way in which we do it is to have the electric field squared minus the magnetic field squared, like this. So this is a term that you have to add, which is the energy of the electromagnetic field itself, not just because of the interaction. So this is the full Lagrangian, and in something known as a covariant notation, where this F mu nu is something that is stitched out of the same mu with various derivatives. Derivatives are needed in order to make this a dynamic degree of freedom. We'll come to this also a bit later. So this is what it is. So all information of scattering will happen only because of this so-called vertex over here. That is, why is it a vertex? A vertex necessarily means that three lines have to meet in order for it to be a vertex, right? So the three lines that are meeting over here is two electron lines and one electromagnetic line, and one electromagnetic field. So I don't know why it got colored blue. So we need a perturbation series, we need free particles, and we need an interaction, exactly as in slide 1. And this is what we do over here. We represent the electron, not just the electron, but the electron and the positron, spin half, both spin half plus minus, loosely speaking by a line, a directed arrow like this. The direction also is important depending on whether you want to discuss electrons or positrons. And then there has to be something that describes the photon also. Yes, tell me.
No, go ahead, please.
Yeah. So a wavy line here stands for the photon. These are just conventions, but it has an evocative idea that the photon has a frequency. An energetic photon, you can drive a really strongly wiggling field, while a long wavelength photon, you can draw it as an undulating field.
The old picture of the electrons as particles and the photons as waves.
Yes. It does cause, but of course we know now that both descriptions are needed.
Yeah.
Both descriptions are valid, and depending on the context. Okay. And then we have this vertex, which is the analog of the lambda v lambda on slide number 1. And everything we do in life now has to be just built out of these very simple rules that were given to us by Richard Feynman. And these are therefore named in his honor as Feynman rules, which will tell you how to do these calculations. In the simplest version, which is quantum electrodynamics, there is an underlying symmetry, which we will also describe later, that is known as a U1 symmetry, which stands for unitary matrices in one dimension. It's a very nice symmetry that was that was basically discovered by Maxwell, who unified electricity and magnetism. There are more complicated versions of this, which rely on larger symmetries, more complicated symmetries that were discovered by Yang and Mills very long time ago. In fact, Yang just passed away at a ripe old age of 103. Amazing person. So, sort of just thought that I would mention it over here. There are analogous rules like this for Yang-Mills theories also, except that the Maxwell field doesn't interact with itself because it is too simple a theory to have interactions. by which I mean the photon does not have any vertex with itself. Okay, so that's what I mean by self-interactions. Whereas the Yang-Mills theories, for instance, the W plus minus and a part of the Z naught together, they all describe a certain SU2 Yang-Mills group. Because you have three of them, W plus W minus, and let me call it W naught, you have the possibility that they can interact among themselves, that you can have a vertex with W plus W minus and W naught. It's not just a possibility, but it actually happens. And it's unique. So these theories, which are based on these symmetries, are the platform on which the standard model is actually built. Okay? So, as I said, at leading order, you have only one term. And if you go back to our slide 1, at next to leading order, you have the possibility of a given in state having an overlap with every possible state also present in the Hilbert space, and you square that matrix element like so. And then you have this energy denominator over here. And the thing is that you have a sum over all possible intermediate states. So we are going from psi n to a certain intermediate state, and from that intermediate state to be with the same psi n over here in this particular diagonal calculation divided by this energy denominator. Why energy denominator? Because everything is going through this interaction potential, right? So in order for you to have an energy on the left-hand side, you have two insertions of the energy, so it had better be divided by one power of the energy in order to be even dimensionally consistent. So this is at order lambda squared. So that's the crucial idea, that you need a sum over all intermediate states divided by something that looks like an energy denominator. So the analogous thing over here is you have, so this is the leading order, nothing more to be done. Supposing at next to leading order, you want to know what happens to an electron that is interacting. In fact, it may not even interact with any external field, because in relativistic quantum field theory, you can have the virtual production of particle pairs or photons and so on. So it doesn't even have to interact with an external magnetic field. But an electron that comes along emits a photon, so that's already one power of the electric charge. But that photon can't go somewhere. I mean, it has to conserve energy and all that. So it carries some energy and then comes back and hits this, so that you have energy conservation at both vertices. But then what was the energy that was carried by this intermediate photon? There's no restriction on that. It's just that the sum of these two has to be equal to the energy of the incoming. So you have to have a sum over all possible intermediate states. In this case, the intermediate states are all free particles, so to speak. So, but I'm just speaking very heuristically. But this sum over intermediate states means that you have to integrate over all possible energies carried by this virtual particle. Okay? Once again, I must warn that many of the things that I'm saying are heuristic. Okay, this is just to get an idea, and this will really, make purists really balk that at the lack of rigor in what I'm saying. But just to get the idea why there should be a so-called loop integral or an integral over all possible energies. Okay, so that's the reason why I have introduced in my first slide the notion of how you have a sum over all possible intermediate states entering the perturbation expansion. And this goes on and on if you want to go to the next higher order in the coupling constant, and the next and the next and so on. So it turns out that at next to leading order, there are basically only three basic diagrams. All other diagrams can be expressed in terms of these. And one of them is called the self-energy diagram, where the electron has a self-energy. Another is called the vacuum polarization. This is a very important idea, that a given photon actually, can split into an E plus E minus pair and merge. This also gives the idea that this electric charge is not always the electric charge, but the electric charge gets shielded by other E plus E minus pairs that are present. So if you have, let us say, a vertex like this, and then there's a vacuum polarization diagram like this over here where the cursor is, that means that this photon may not be seeing all the electric charge that is available. if it's a very energetic photon. So that's what leads to the next idea, which is that of renormalization group, which says that energies actually can, that coupling constants can actually run, that the vacuum actually shields the electric charge. That's called the renormalization group flow. So I think we have reached a point where probably I should stop, and
Yeah, I
we
think
take
this
this
would be a
later.
good place to stop for today, and we'll
Yeah.
yeah can
Yes.
continue next time.